So it says we have already applied interest formulas to compound continuously, and we used PE to the RT for our interest formula. So it turns out that this formula is an example of this general format. A equals A sub 0 e to the kt. A sub 0 just means your initial amount. So we used P to represent principal. Principal is the initial amount of money. A sub 0 just means initial amount, but it can be used for other exponential functions. So A sub 0 is the original amount, K is a constant, and T is time. If K is positive, then it's an increasing function. If K is negative, then it's a decreasing function. Increasing might be compound interest, population growth, exponential decay might be radioactivity, radiocarbon dating. So like when you find a bone or remains, how do you know that it's 20,000 years old? How do you know it's 100 years old? Or card depreciation. So the value of your card depreciates every year exponentially. So the simplest thing might be I give you a formula and you just have to plug in T for time. So you already know the initial size of an insect population. E is just representing that uninhibited growth or decay. So E is used because in science it does represent that uninhibited growth. And then 0.02 is their constant, and T is representing time in days. So they just want you to plug in 1 week. So what are you going to plug in for time? If T is time in days, you're going to plug in 7. So you're going to calculate on your calculator 500e to the 0.02 times 7, and that will tell you your new insect population after 1 week. So we're using a complicated formula, but it's a relatively easy process because you're just plugging in the number of days. Around to the nearest insect. 575? Did you get that okay? You know where the E button is over the divided by sign, right? All right, so it says sometimes we know the value of the current population, we know K and we know T, but we need to solve for the initial population. So it says in these cases, remember, although it may look intimidating, E to the KT is just a number if you know K and T. And we did this with interest where we could divide something to the other side. So the size of an insect population has reached 10,000 organisms. A researcher determined the value of K for this population growth is 0.05. What was the population 3 days ago? So we know 10,000, but we don't know the initial population. So this constant just stands for initial population. It doesn't mean plug in 0. 0 is not the number. 0 is just a variable. And we know that the K value is 0.05, and we know that it's been 3 days. So if we're trying to get A sub 0 by itself, we're going to divide both sides of the equation by this number. So in the description, it said E to the KT is just a number. So you can calculate this number on your calculator and then divide it to the other side of the equation. Whatever you're going to get, you take 10,000 and divide by that number. So do E to the 0.053 and then do 10,000 divided by your answer. I just wanted to show you, I did it 2 different ways. First, I just typed it in, 10,000 divided by E to the KT, got the answer. But if you want to, you can just do E to the KT, get your answer, then take 10,000 and divide by the exact answer. Don't round this number 1.16. You want to have the whole answer. So you should get 8607 as your initial population. Obviously, if this is growth, our initial population should be smaller than what our current population is, right? All right, so you're starting to get more familiar with the equation and what the parts of it are. So now the most common problems involve finding the value of K. Because if you think about it, if you've got some bones of a whatever type of animal or human or whatever, and it's in a different condition, lost in the desert, under sand, under the ocean, in ice, right? The K value is going to be a different rate of decay over time. So your K value needs to take into account like the environment, how fast are things happening. So the process of carbon dating involves finding the value of K. So they're talking about a leaf, and they did some carbon dating, and they found out that the leaf contains 30% of its normal carbon-14. How old is the leaf? So you first need to figure out the K value for carbon-14, and it tells you the half-life of carbon-14 is 5,600 years. So have you ever heard of a half-life before? A half-life is for like radioactive elements that are losing part of their, what are they called, atoms? What are they losing into the air? Their mass, right, over time. So if you started with like 100 grams of like uranium or whatever is leaked out of this power plant, in a half-life, so in one half-life, you would still have 50 grams of it left. So with like uranium or some of that bad stuff, its half-life might be 100 years. 100 years is a long time for something to decay and still have 50 grams of it left. This has a half-life of 5,600 years. So it would take 5,600 years to reduce the amount of carbon by a half. Then it's going to take another half-life to get 25 grams or 25%, depending on what you're starting with. So a half-life could be really short. If half-life is like an hour, in the matter of a day, all the stuff's going to be gone. But if a half-life is really long, it's going to take a long time for that to disappear. So first it says we have to find the value of K. So if this is a half-life situation, they didn't tell you how much you start with. We're going to pretend that we started with 100 grams because 100 is an easy number to start with because half of 100 is 50. I'm making up the original amount. I don't think a leaf really weighs 100 grams. So I'm making up the starting weight and the ending weight because they're telling me this is a half-life issue. So that way I can just cut it in half. E, I don't know K, but I know that it takes 5,600 years to go from 100 down to 50. Now I can solve this for K using properties of logarithms. What would be my first step to get K by itself? So my first step is to get this by itself because then I could change this into a log. So my first step is actually to divide 100 to the other side. And you're going to be using this process every time you need to solve for one of these exponents on this worksheet. So get used to dividing this number to the other side. So you get 0.5 equals e to the k times 5,600. And then you're going to convert it into a log. So you're going to get really good at going from exponential world into log world. So in log world, the base of the exponent becomes the base of the log. So that's actually the natural log, right? Of 0.5 equals k times 5,600. If I read this back, e is the base, k times 5,600 is the exponent, and 0.5 is the solution, right? So these should be equivalent statements. So I can just take the natural log of a half on my calculator, and then at the end, divide by 5,600 to find K. And you're going to get a really small number that's given to you in scientific notation because it's so small. So you may be unfamiliar with how to read this number on your calculator. Negative 1.24. E to the negative fourth means that you're sliding this decimal place 4 places to the left. So if you wanted to write out your K value, it's negative 0.000124. See how that's sliding it 4 decimal places to the left? So your K value is really tiny because the half-life was so long, and K is negative because we're losing material over time. So you just did all that work to solve for K. But this process doesn't change for any of the other applications. So You need to get used to like dividing by the number, switching into log form, and finding K or T, whichever one you're solving for. So now it says, oh, now we can use the formula to actually figure out how old our leaf is, right? That's why we wanted K. So now that I know the rate that carbon-14 is decaying, I can go back to my situation when I have 30% of the leaf's mass or carbon. And do you see how they already wrote this out for you? We had written out 50 equals 100. So they had basically already written out 30 equals 100, and they've already divided by 100 on both sides. So see how they're starting with this equation? So they're doing 0.3 equals e to the negative 0.000124 t. We're going to try to solve for t this time. And we're starting with 30% of the carbon. So they already made up 30 and 100 as our numbers, our starting number and our ending number. And they already divided by 100 on both sides to get to 0.3. So you're going to follow the same steps we just did, change it into log form, and then this time we're going to divide by the K value to get the T value. So I'm going to rewrite this in log form. The base of the log is E. The inside number is going to be that 0.3. And then I have that long decimal times T on the right-hand side. So this time, instead of dividing by 5,600 years, I'm going to divide by my K value. And that will give me how old the leaf is. I know that it's old, right? It's older than a half-life. It's not older than 2 half-lives, because that would be 25% of its carbon. So it's got to be right around like 10,000 years about. And I just want to show you, this was the natural log of 0.3 divided by my rounded K value. This is the natural log of 0.3 divided by the unrounded K value that I grabbed from up top. I mean, they came out to roughly the same number of years, 9,700, but the rounded value came out to 9,709 and the unrounded K value came out to 9,727. I would count them both correct on a test or a quiz, but you need to write down what your K value is so that I can double check that your answer makes sense for your K value. So I'm going to put the exact answer, 9727, but if you wrote just the K value down, you might want to put 9709. But the exact value is 9727 years old. So that's an intro to some applications. Newton's law of cooling, I'm going to hold off on until tomorrow because that's a little bit more complicated equation. I would rather us go to this guided practice, these 3 questions on the next page, and see if we can work through them a little bit on our own, setting them up, figuring out how to do the calculation for the half-life, and then I can walk around and help you on those. Because I know that using this equation is really challenging. So I'd like you to try to do these 3, and then there is a question on the back page, number 5, that you can do when you're done. Let's skip number 4 for today. I'm going to do Newton's law tomorrow. So try 1, 2, 3, and 5, and I'm going to walk around